Hello students, I welcome you in today's session of physics. And in physics, you know very well, we were discussing a topic work, power and energy, which is your chapter number 9. Clear? This is your we had already covered most of its topic of this chapter in our two previous lectures. This is your lecture number 3, and in today's lecture we are going to discuss different forms of energy you can see here. I hope you know very well what are mechanical energy. I told you in the previous lectures. Mechanical energy are of two types. First one is your kinetic energy and the potential energy. We had also discussed about the kinetic and potential energy in our previous topics. Clear? After that, we had covered the free fall under the gravity. Now today, you can see here, we were starting from here. So kinetic energy and potential energy are the forms of mechanical energy, as I told you. So various other forms of energy are known as heat energy. Clear? After that, you can say it internal energy, electrical energy, chemical energy and nuclear energy. So these are the forms of energy. So first we'll discuss about the heat energy. What is heat energy? So a body possesses heat energy by virtue of its random or disorderly motion of its molecule. It is related to the internal energy of the body. What is does it mean? It means that if you provide external heat to the molecules of an suppose you provide the heat to the liquids or as well as gases. So the molecules doing start comes to the random motion, or you can say that the zigzag motion. Clear? So due to the random motion, a heat energy is produced. Fine. Now come to the internal energy. So every material body is made up of large number of small particles called molecules. So a body possesses potential energy by virtue of the particular configuration of its molecule against the intermolecular forces. Clear? I told you about the potential energy, the energy which is due to the position of the body. So that is the thing written here. And the kinetic energy because of the random motion of its molecule. So the sum of the kinetic and the potential energies of all the molecules of the body is called its internal energy of the body. Clear? The internal energy of a body depends on its temperature. This is the important one. Kindly remember it. So as the temperature rises, the random motion of the molecules of the intermolecular and the intermolecular distances both increases. So this causes increase in the kinetic as well as in the potential energy of the molecule, and hence the internal energy of the body. Clear? Now come to the electrical energy. So it arises because work is done in moving free charge carriers in a particular direction inside a conductors. Fine. I hope you know very well why the current is produced due to the random motion of the free electrons in the molecules. Now come to the chemical energy. So it is the energy which is possessed by a chemical compound by virtue of the chemical binding of its atom. A chemical compound has less energy that possessed by its constituent parts. Fine. So this difference is the chemical energy which is released when a chemical reaction takes place. Clear? Now you can see here we are going to discuss about nuclear energy. So this energy arises in the nuclear reactions either by fission. I hope you know very well what is fission and fusion. There are the two kinds of nuclear reactions. One is fission and another one is fusion. So what happened in the fission? By the fusion of heavy nuclei into lighter ones. In fission process, a heavy nuclei is break down into the lighter nuclei, while in fusion, a lighter nuclei combine together and form a heavier ones. Fine. So the huge amount of solar energy comes due to the fusion reaction going on inside the sun. Fusion is an important nuclear process which is responsible for the production of energy in atomic power plants. Clear? Now we will move to our next topic, which is the mass energy relation equivalence. You can see here this thing we are going to discuss now. So till the beginning of the 20th century, you can see here, it was believed that the matter and energy had two different entities, and that like energy, the mass of the universe is also conserved. Now, who's defined it? The Einstein for the first time established that the mass and energy are two different forms of the same entity and they are interconvertible. He gave mass energy equivalence relation, which is your E is equals to mc square. This is a very famous formula where E is the energy obtained when a mass small m is placed or converted into energy, and c is the velocity of light, I hope you know, which is equals to 3 into 10 to the power 8 meter per second. This relation indicates that an enormous amount of energy is obtained when a complete conversion of very small amount of mass. Clear? Now come to the transformation of energy. This is the next topic, the transformation of energy. So energy exists in various forms. In many physical processes, energy changes from one form to the other. For example, in electric heater, electrical energy is converted into which? heat energy. Same thing, steam engine changes heat energy into mechanical energy. The loudspeaker convert electrical energy into sound energy. An electric bulb, electrical energy is converted into light energy. Burning of coal or oil, chemical energy is converted into heat energy. So these are the conversion or transformation of energy. Now come to the power. I hope you are familiar with the power. The rate of doing work is known as power. So this is the definition of power. The rate of doing work by an agent or machine is called the power of the agent or the machine. Fine. So you can write it like this: P is equals to W by T, or work upon time. This is the formula for the power. So if an agent does a total amount of work W by an exerting a force on a body for the total time interval T, then you can write it: the average power delivered by the agent is equals to how much? P bar is equals to W by T, where bar indicates the average power. If you or in case instantaneous power delivered by an agent, you can write like this formula: P is equals to dW by dt, where what is dW? dW is the work done in infinitesimal time interval, which is dt. Clear? So if the power is constant in time, then P is equals to how much? Is equals to the average power. Here you can see that it is written here. So as the power is the ratio of two scalar quantity W and T, so the power is also a scalar quantity. Fine. Now the power delivered to a body can also be expressed in terms of force applied to the body and the velocity of the body. So we know that the work done by the force F in the displacement ds of the body is dW equals to F dot ds. So you can write it this formula from this above relations: dW by dt, P is equals to dW by dt, and in place of W you can write this equation: vector F dot ds vector by dt. Now force is a constant term, so we represent, you can see here, ds by dt is the displacement upon time, which is comes out to be changes into velocity. So this formula P is equals to F dot V. Fine, which means power is related to the force and the velocity. So the power of an agent is the dot product of the applied force to a body and the velocity produced in the body. So this is the definition. Now what happens if the direction of force and the velocity are parallel? In that case you can write it the magnitude form: P is equals to Fv. And if they are anti-parallel, means the velocity and the force both are anti-parallel, that means there is an angle between 180 degree between them. So you can write it P is equals to vector F dot vector V, or you can say that Fv is equals to Fv cos 180, that is your minus Fv. The power comes out to be negative when an agent exerts a force on a body in a direction opposite to the displacement, hence opposite to the velocity of the body, then he does negative work on the body, delivers a negative power to the body. Now here you can see that these are the dimension and the units of the powers given here. So I hope you know very well what is the unit. The unit of power is watt, or you can write it 1 joule per second. Clear? And this is the dimension ml square t minus 3. Now we will moving to our next topic, which is the collision. You can see here, this is collision. Now what is collision? So collision between the two bodies or the particles is said to occur when they either physically strike against each other, or if the path of the motion of one is influenced by the other. Clear? So collision between the two billiards balls, carom, coin, automobile are example of collision in daily life. In a gas, the molecule keep on colliding against each other. In physics, for collisions to take place, physical contact is not necessary. Two particles are said to collide even when one particle influences the motion of the other. So such influence may be due to the long-range gravitational, magnetic or electrostatic forces. Clear? Or you can say it, or short-range nuclear forces. So you know very well in chemistry, you had read about the Rutherford alpha scattering experiment. The alpha scattering is scattered due to the electrostatic force of repulsion between the alpha particle and the solid nucleus. So there being no physical contact between the alpha particles and the nucleus. So when two bodies collide, they exert interacting forces on each other which are equal and opposite at all instants during collision. As soon as the collision is over, the interacting forces become zero. Clear? Now here are some types of the collision given here in your book. You can see here, the first one is the elastic collision. I am not going to the deep section because I am just taking in a brief. Elastic collision and elastic collision. So first we are going to discuss about the elastic collision, which is in one dimension. So what happening here, you can see that, let us consider two elastic bodies. First one is your A and the other one is your B. respective masses m1 and m2 moving along the same straight line path with a velocity of how much? Initial velocities u1 and u2, you can see here. If u1 means the initial velocity of the first mass is greater than the second mass, then the body A and B collide head to head. You can see here the figure number B. Now suppose v1 and v2 with the final velocity after striking or after collision. So they are moving with the velocity. From the figure C you can see that they are moving with v1. First one is v1 and the second one is the v2 velocity. And here they are striking with during collision. This is the before collision. Clear? I hope you understand all the three concepts. So by the law of conservation of momentum, you can see that the law of conservation of momentum, m1 u1 plus m2 u2 means the energy or momentum before collision equals to the momentum after collision. P is equals to mv, you know very well which is the momentum. So since all the velocity are in the same direction, so we can write the above equation in terms of the magnitude of u1, u2, v1 and v2. So if we write in terms of magnitude, so you can see that this is the equation comes out. Clear? Now since the collision is elastic, so the kinetic energy of the body is also conserved in the collision. That is, you can write it the kinetic energy. This is the kinetic energy, half mv1 u1 square. So after solving out, you can see that this is the equation we are getting here. Now if we divide, this is equation number second and this is your equation number 1. So what happens if we divide equation 2 by equation 1? So if you divide it, then you will get the relation like this: u1 minus u2 equals to v2 minus v1. Clear? Where u1 minus u2 is the relative velocity with which body A and B approach each other before collision, and v2 minus v1 is the relative velocity with which the bodies separate from each other after the collision. So you can say that the relative velocity with which two bodies approach each other before collision is equal to the relative velocity with which they recede from each other after collision. Fine. Now there is an expression given here. We can now find out the final velocity, which is v1 v2 of the bodies A and B in terms of their masses m1 and m2 and initial velocity u1 and u2. So you can write it v2 is equals to u1 minus u2 plus v1, and if you put the value of v2 in equation 1, which we already find out in above expressions, then you get here v1 is equals to here this much m1 minus m2 by m1 plus m2 of u1 plus 2m2 by m1 m2 by u2. Clear? So this is the expression for the velocity v1 of body A after the collision. Similarly, if you put the v1 in place of in equation third and from equation third in first, so you can see that this is velocity v2. This is the expression for the velocity v2. Clear? So this is the expression for the velocity v2 of the body B after collision. It can also be written by the expression of for v1 equation 4 by replacing m1 and m2 and u1 by u2. There are few special cases given here. What are the cases? First, see the first one. If the mass of the colliding bodies are equal, means if the two bodies are of the same mass, then from the equation 4th you can write it like this: v1 is equals to u2 and v2 equals to u1. Clear? That is, in a one-dimensional elastic collision of two bodies of equal masses, the body merely exchange their velocity after collision. Means they are moving with the same velocity before collision and after the collision. Now what's the special case number 2? You can see here, if the target body B is initially at rest, means the second body which is of mass m2 is at rest, that its initial velocity is 0. So from the equation 4th and 5th you can say that v1 is equals to this and v2 equals to this much. So in this case we consider three situations. Now what are the three situations? You can see here. The first one, the two bodies are of equal masses m1 and m2. So from equation 4th and 7th we have v1 equals to 0. Clear? And v2 equals to u1. Fine. That is, when a moving body suffers one-dimensional elastic collision with another body of the same mass at rest, then the first body is stopped cold and the second body begins to move with the original velocity of the first body. So both the momentum and the kinetic energy of the first body are completely transferred to the second body. I hope you understand it. Now I am coming to the second one. The target body, which is B, which is at rest, is much more massive than the colliding body A. That m2 is very much is bigger than the first one. So you can see that there is an expression changes to like this: v1 is approximately equals to minus times of u1 and v2 is equals to 0. That is, when a light ring moving body suffers a one-dimensional elastic collision with a much heavier body at rest, the lighter body rebound with its own velocity while the heavier body remained practically at rest. So a ball drop on the earth rebound with the reverse velocity approximately to the same height from which it was dropped. Now see the C1, the target body B which is at rest is much lighter than the colliding body which is your A, that is M2. If very much smaller than M1, then what happened here, you can see that V1 is approximately equals to U1 and V2 is approximately equals to the 2 times of U1. Clear? So that is, when a moving body collide with a much lighter body at rest, the heavier body continue moving with the same velocity while the lighter body is moving with approximately twice the velocity of the heavier body. So that is the thing written here. Now you can see here there is an inelastic collisions, an elastic collision. So this thing you can read by yourself. This is not so much important thing. I am skipping this and moving. This is also you have to read loss of kinetic energy during elastic collision. I am coming to the elastic collision in 2 dimension. Now this is the important one. So I am going to discuss this. So suppose an elastic body of mass m1 with a velocity moving with a velocity u1 along a straight line, say x-axis, and collide with another elastic body m2 which is initially at rest, as shown in the figure. You can see here, this is the figure, and with this figure you can easily understand what is going on. Clear? So that is the thing. So after collision, the bodies m1 and m2 move with the velocity v1 and v2 in the xy plane, making an angle theta1 and theta2 respectively with the x-axis. So by the law of conservation of linear momentum, you can write it like this: m1 u1 equals to m1 v1 plus m2 v2. Now let us consider here the scalar component of u1, v1, v2 along the xy directions and apply the law of conservation of linear momentum separately for the xy component of the motion. So you can see here, this is the expression is formally formed. This is equation 1 and equation 2. Now since the collision is elastic, so the kinetic energy is also conserved. So you can see that this is the expression for the kinetic energy, and this equation comes out to be third one. So from equation 1, 2 and 3, we may assume that m1, m2 and u1 are known, but the motion after the collision involve 4 unknown quantity, which is your v1, v2, theta1, theta2, which all cannot be determined from these equations. So at least one of them should be given. So for example, for a given value of theta1, the quantities theta2, v1 and v2 can be computed from the equations. Clear? This is the important one. What is the coefficient of restitution? It might be asked in your examination. So you should know what is the coefficient of restitution. So in a daily life, most of the collision are either perfectly elastic nor perfectly elastic. Clear? So in this, kinetic energy decreases and hence the speed of the separation is less than the speed of the approach. So the degree of elasticity of collision is measured by the coefficient of restitution. So this is the important one by which we measure the coefficient of elasticity or elasticity of collision. So you can say that the coefficient of restitution is the measurement of the elasticity of collision. So it is defined as the ratio of relative speed of separation after collision to the relative speed of approach before collision. Thus value of E depends upon the material of the colliding body. So here you can see that this is the important one written here. For perfectly elastic, coefficient of restitution equals to 1, and for perfectly elastic, coefficient of restitution collision is equals to the 0. Clear? So please remember this one. So students, you can see here, this is the end and the last topic of our chapter, and after we are from this, I am winding this session. I hope you understand it whatever I taught you in our previous lecture and in this lecture as well. So if you have any doubt, kindly ask me in the comment section. Till that, do study. Thank you class. Thank you very much.